Mean square error convergence and almost sure convergence are both strong senses of convergence. In a previous lecture, we showed that almost sure convergence does not, however, imply mean square error convergence. Now we'll show an example which shows that mean square error convergence does not imply almost sure convergence, or convergence in probability 1, in other words. So for that, we'll take a sample space, which is real numbers between 0 and 1. Okay, and we'll define intervals a n such that the random variable xn of w is going to be equal to 1 if w is in the region an and 0 otherwise. Okay, so the region an is going to be a subset of 0 to 1. The first an is going to be the whole interval. The second an is going to be half of this half, the first half of the interval. The third one will be the second half. And then the interval will keep moving around with n while its size shrinks in the following way. We can always, so basically we'll define an as the interval k times 2 to the minus h to k plus 1 times 2 to the minus h, where h and k are defined in the following way. Every integer n can be written as 2 to the h plus k, where k and h are integers, positive integers, and k is less than 2 to the h. I should say positive union 0. Okay, so accordingly, for example, if n is 1, h is 0, and k is 1. Okay, so the interval a1 is going to be the interval from 0 to 1. So if n is 2, h is 1, k is 0, and a2 is 0 to 1 half. So if n is 3, right, if n is 3, h is 1 and k is also 1, a3 is 1 half to 1. If n is 4, h is 2, k is 0, a4 is 0 to 1 over 4. Okay, so now the size of the interval has shrunk by half. And n is 5, h is again 2, k is 1, a5 is 1 over 4 to 1 half, and it goes like this. So the size of the interval is halving, and the interval keeps moving around. So if we want to plot, for example, as a function of w, x1 of w, x1 of w is equal to 1 for all values of w. On the other hand, x2 of w is 1 up to 1 half and 0 for values of w after 1 half. Let me draw x3 on a different plot. x3 of w is going to be 1 for values of w after 1 half. On the other hand, x4 is 1 for values of w up to 1 over 4 and 0 otherwise. And finally, for example, let's draw x7 and x9, just two arbitrary examples. x7 of w, for example, will be 1 here from 7 over 8 to 1, and x9 is going to be from 1 over 8 to 1 over 4 . So basically what happens is when you fix a given w, for example, you fix a w here, let's call this w sub 0. Okay, the sequence x of w0 goes like, originally it's 1, and then it's 1, and then it's 1 for a while, and then it becomes 0, 0. I may not be doing this exact, and then becomes 1 again, and then 0, 0, 1, etc. So what happens is 1s will keep popping up as n increases, no matter how large n becomes. So there is, in fact, no value of w for which the sequence will stay constant at 0 after a certain amount of time. So 1, the value 1 will keep popping up infinitely often. All right. So, so basically because of this, we can write that w such that xn of w converges to 0 is the empty set. In other words, xn does not converge in the almost sure sense, or in with probability 1 to 0. Okay, but on the other hand, think about the expectation. Think about the expectation of xn minus 0 squared. Expectation of xn squared is 1 times the probability that xn is 1 in this case, but the probability that xn is 1 goes like 1 over log n, because for every n, the width of the region where xn is 1 decays like log n. So this is like 1 over log n, which goes to 0. Okay, so then xn does converge in the mean square error sense to 0. Okay, so this example shows that mean square error convergence does not imply almost sure convergence.